So welcome everyone to this ANITA lecture. My name is Darren Croton. I'm a professor at Swinburne University, and I'm also part of the steering committee for the Australian National Institute for Theoretical Astrophysics. And once a month or thereabouts, we run an online lecture series, and our target audience basically undergraduate students, postdocs, and interested faculty. And we cover some very basic astronomy topics all the way up to more advanced specialized topics. Today, it's my great honor to introduce again David Wilner from the Harvard-Smithsonian Center for Astrophysics. David gave last week's lecture on radio astronomy fundamentals, and he's following up with a second lecture this week on imaging and deconvolution in radio interferometry. Just to note that at the Google Plus page, we have posted the slides. So if you're having trouble following on the screen, you're quite welcome to download the PowerPoint presentation and follow from there. Well, actually, I think it was a PDF, and you can follow from there. So without further ado, I'm going to hand it over to David, and I hope you enjoy this second lecture. All right. Thanks, Darren. Welcome to the second lecture in our series on radio astronomy and interferometry. The second lecture is going to focus on imaging and deconvolution in radio interferometry, picking up more or less where we left off last time. The first lecture dealt with radio astronomy and interferometry fundamentals. I have the outline here, a brief introduction to radio astronomy and emission mechanisms, and leading into definitions of interferometry, visibilities, and some intuition about Fourier transforms. This lecture is going to focus entirely on imaging and deconvolution in radio interferometry. And after a brief review of where we left off last time, I'll go into a formal description of the imaging process. I'll talk about some practical considerations in imaging and making radio interferometric images, including visibility weighting schemes. And the latter part of the lecture will deal with deconvolution methods and algorithms and missing information. As before, my intent is not to be entirely rigorous, but instead to give you a feel for the issues involved in this case, imaging and deconvolution in radio interferometry, and I'll direct you to some references if you want more information. So the next slide has some of these references. I discussed them in more detail in the first lecture, so I'll go through them quickly. The first is the Essential Radio Astronomy course, which is an entire radio astronomy course available online from the National Radio Astronomy Observatory. The second is the reference book, Thompson, Moran, and Swenson on interferometry and synthesis in radio astronomy. That probably has a derivation of anything that you're wondering about, and it is a fantastic book. There are a couple of summer school workshops that have very extensive proceedings, in particular the NRAO synthesis imaging workshop. And indeed, many of the slides that I'll show today are taken directly from my lecture at the NRAO Synthesis School, and you'll be able to recognize those by the master with the NRAO and the New Mexico text on the bottom. The IRM Interferometry School proceedings, I think, are also really excellent, give a somewhat different take, and I direct you there. And of course, there are many others on the web that you can find yourself. All right, so a brief review of interferometry. We have our two radio telescopes, 1 and 2, looking in some direction at a source in the sky. We delay the signal from one so that we can multiply them and integrate the signals, and we measure something that we call coherence, which is related to the brightness distribution in the sky that we're interested in, but is not exactly the brightness in the sky. The schematic is implemented in a lot of different ways. Here are some pictures of aperture synthesis telescopes, interferometers that work at millimeter wavelengths. So on the left, we have the Jansky Very Large Array, the new ALMA telescope in Chile. On the right, we have the SMA, the Australia Telescope Compact Array, the Aram Plateau de Bure Interferometer, and the Karma Telescope in California. All of these have different number of elements, different sizes, different baselines, different configurations, but they all do the same thing, which is measure visibilities from the sky. So to remind you, here's the key equation. The visibility, the complex visibility function, is the two-dimensional Fourier transform of the sky brightness distribution, which I call T. And there are some restrictions on this. The emission needs to be incoherent, the field of view needs to be small, the source needs to be far away. There are various things, and if you're interested in all the details of that, then I direct you to Thompson, Moran, and Swenson, particularly chapter 14. So mathematically, this visibility, which is a function of spatial frequencies, U and V, measured on the ground in wavelengths, is this double integral of the sky brightness times a bunch of sinusoids, that's the e to the 2 pi factor, over the angles in the sky, L and M, which are measured in radians. And so the shorthand notation I have for this is that the visibility of U and V is the Fourier transform of the sky brightness T of Lm. And of course it goes the other way as well. So that's the one key equation. The visibility is the Fourier transform of the sky brightness, and we're going to build on that. So the basic idea of interferometry, as I discussed last time, is to sample this visibility function at enough points in this UV plane using distributed small aperture antennas at different baselines to synthesize a single large aperture, which goes out through the longest baselines. So one pair of antennas gives you one baseline. It gives you two samples of the UV plane because the sky brightness is real. And if you have n antennas, then you get n times n-1 samples at a time. If you let the Earth turn, in fact, you can't stop the Earth from turning, then you fill in the UV plane over time. That was part of the Nobel Prize of Sir Martin Ryle. And if you want more UV coverage, then you might move your antennas around to get different baselines and different samples. And you might be able to observe even at multiple frequencies, because you remember U and V are measured in wavelengths, if you can understand how the source brightness distribution changes with frequency. Maybe you can characterize that simply. And of course, an important assumption is that the source isn't varying as you make all these measurements, because that will mess up the information that you're getting. Okay, so you make these measurements of the visibility, but what you're really interested in is the sky brightness. So ultimately, you might want to make an image. So let's talk about what that means. So we have this equation. The visibility is the Fourier transform of the sky brightness, and we're sampling the Fourier domain. We're sampling that visibility function at discrete points, U and V, and we can represent that by this function capital S. That's the sampling function. Is just the collection of points where we make measurements of the visibility. So if we Fourier transform now the sampled visibility function, that is the visibility times the sampling function, we get something which is not exactly the sky brightness, but some modified version of the sky brightness, which we call TD. And if we apply the convolution theorem to that, remember the product in one domain is a convolution in another domain, then we get that the visibility, which transforms to the sky brightness, convolved with the Fourier transform of the sampling function gives us TD. So this small s, this Fourier transform of the sampling function, is usually called the point spread function. And so what this means, this equation means, is that the Fourier transform of the sampled visibilities yields the true sky brightness, T, convolved with the point spread function. And the radio jargon for this is that the dirty image, that is that TD, is the true image, T, convolved with the dirty beam, or the point spread function. So that's the formal sort of mathematical description of what the imaging is. And I think it's much easier to understand if you see some pictures. So let me go through some pictures. First, the sampling function. This is a repeat of the sampling function that I showed you in the first lecture. So this is from the sub-millimeter array on Mauna Kea. If you imagine putting 6 of the antennas at these locations, observing at a frequency of 345 gigahertz, source at a declination of plus 22 degrees, then the samples in the UV plane turn out to be this. And this is an actual observation. The fact that the lines are not entirely continuous but dashed is because the observations go off to calibrators every now and then. And the fact that there are some gaps means the array stopped working for a while for one reason or another. But you have this irregular sampling of the Fourier plane, U and V, here measured in thousands of wavelengths, kilolambda. If we put the antennas in a different configuration, now a little closer together, that's the red locations, one gets some different sampling on a different day of observations. And putting them even closer together, one gets a different sampling, now of even shorter baselines. And putting all that together, this is the sampling of the visibility plane that we've done with 3 configurations of the SMA. All right, so that's kind of an odd bit of sampling of the Fourier plane, but that's what it is. And that's typical for an array like the SMA or the others that I showed you. So let's think about that formal description again. This pattern in the UV plane is our capital S, our sampling function. If we Fourier transform that, then we get our point spread function, or in the radio jargon, the little s, our dirty beam. And you can see it's something that's concentrated in the center, but it has lots of structure all around it, and that's from the missing samples in the UV plane. If we convolve that with some brightness distribution on the sky, this is some arbitrary brightness distribution. It is a little disk-like thing and a little point source. It's just something that we imagine is the brightness in the sky. Then we get an image that looks like the following. So this is the dirty image using the sampling that we got for this observation. And you can see that the dirty image bears some resemblance to the actual sky brightness, but it's corrupted by all of the structure in the point spread function, which comes from the sampling in the UV plane. So you can see that if you have better sampling in the UV plane, you're obviously going to get a better image. It's interesting to think about, how that happens. So let's talk about that dirty beam shape. If you just have 2 antennas, one pair of antennas, and you make one sample, then you get a fringe pattern on the sky. So here on the left, I'm showing the UV plane sampling, and on the right, I'm showing the point spread function that you get by Fourier transforming that distribution. So 2 points, one baseline, essentially gives you a fringe pattern. If you add another antenna, well, now we have 3 antennas, so that's 3 baselines, and you can see your point spread function now looks different. It's getting a little more concentrated in the center, but it's very much a checkerboard pattern. If you have more antennas, you can see your point spread function is starting to shape up. You add another antenna, it's looking even better. One more antenna looking, now starting to look like a reasonable point spread function. Another antenna, even better. Unfortunately, now you've run out of working antennas, so you're not going to get better unless you can buy some more antennas and deploy them. So what can you do? Well, you can take more samples. You can let the Earth turn, and so say after 10 minutes, your point spread function gets a little better because you have more samples. Maybe you go for 20 minutes or an hour, things starting to get better, and 3 hours even better, and 8 hours even better. So I'm going to just step back through that so you can see how the point spread function improves. Add an antenna, add more antennas, it gets better. Over time, it gets better until you go through a full track on the sky, and you have something that actually looks pretty reasonable in terms of the sampling on the UV plane. So you can see that these modern interferometers, in particular ALMA, which has over 50 antennas, will have many, many baselines instantaneously, and you can really fill in the UV plane tremendously well. So assume you make your observation and you have your visibilities. What can you do with them? So one thing you can do is not make an image at all. If you know something about your source, you may just want to fit the visibilities directly. So this is good for simple structures. If you had say a single point source, or a collection of point sources, or something you knew was a symmetric ring, or something like that, you could just make a simple parametric model and fit the visibility samples directly, right? You can Fourier transform your brightness distribution and fit the visibilities directly. Or if you're interested in some statistical description of the sky brightness, say you're interested in the fluctuations that you see, you might do a better job just fitting the visibilities directly rather than going through the imaging process. And it's nice that visibilities, which are what you measure directly, have very well-defined noise properties. And so if you're interested in the uncertainties on your fitting parameters, it can be very useful to directly analyze your visibility samples. But more often than not, you have something that's more complicated. And so what you'd like to do is recover an image. But you have incomplete and noisy samples of the Fourier transform of the image, and that's what you need to analyze. So, like I said, you take the Fourier transform of your sample visibilities, and you get your dirty image. But I hope it was obvious from the previous example, it's not so easy to do science with the dirty image. So often, what you need to do is deconvolve the point spread function from the dirty image to determine some model of the sky brightness and work with that model. So that requires some assumptions, and we'll get to that. So first, some details of the dirty image. I've said for the last few minutes, well, we take the Fourier transform. Well, what does that really mean? In practice, almost all the software packages that do this use some form of a fast Fourier transform algorithm because it's a lot faster, hence the name, and it's simpler in a way than direct Fourier summation, right? If you were to actually take every visibility and multiply it by a sine and a cosine, that's a lot of operations. And it turns out that for a 2 to the n by 2 to the n image, these FFT algorithms are order n log n, and so you really save orders of magnitude in time. The downside of the FFT algorithms is that you need the data on a regularly spaced grid in order to do the Fourier transform this way. And the data does not come on a regularly spaced grid, right? Aperture synthesis gives you the samples that it gives, depending on telescope geometry, where the source is in the sky, and when you observe it. It doesn't ordinarily give you a regularly spaced grid. So one thing you have to do in order to do a fast Fourier transform is to grid the visibilities. So a process of gridding is used to resample the visibilities onto a regular grid. So imagine you put a regular grid down on your visibility samples. So it's customary to use a convolution method to do this. There are a lot of different ways one can imagine doing this. And the way it's typically implemented is to use special functions for the convolution, so-called spheroidal functions, that both minimize smoothing and minimize aliasing. So I'm not going to discuss this in any great detail, but I just want you to know that the visibilities that you end up Fourier transforming are the true visibilities times the sampling function, then convolved with a gridding function. So the image you get, the dirty image, is really the dirty image multiplied by the Fourier transform of the gridding function. So just know that the gridding function is in there, and you can imagine trying to divide it out, although that's generally not done. Okay, another detail is the antenna primary beam response. So on the right here, I have a schematic of a radio telescope, and as we discussed in the first lecture, it has a primary beam, a half-power field of view, half-power beam width, related to the number of wavelengths across the diameter, lambda over d. And the response of the telescope is not uniform over the whole sky, it's directional. So the antenna response is modifying the sky brightness distribution. You know, typically it's something which approximates a Gaussian. There's a taper, and the directional response falls off as you go away from the axis of the telescope. However, the telescope often has some response in addition to the primary beam. There are so-called side lobes, and the response is usually much lower than the main lobe, but if you have very bright sources around the sky, they show up in the side lobes, and so that can be important. So it's something that is an issue that can come up. And as I said, the antenna beam modifies the sky brightness. Basically, the sky brightness is multiplied by this beam pattern. So you can correct for that just by dividing out the beam pattern in the image plane, which is fine. If you have large sources, that is sources that are much bigger than the half-power beam width, then you need multiple pointings of the antenna to cover the source, and this is usually called mosaicing. So at the bottom right here, I have a picture of a sky brightness distribution. Remember, this is our astronomer. If you're observing this with the SMA at 345 gigahertz, the 6-meter antenna, the whole astronomer fits inside the primary beam. You're happy. She might be a little bit attenuated at the corners, but you can correct for that by dividing out the primary beam response. But if you were to observe this brightness distribution with ALMA at the same frequency, or say at twice the frequency, then the primary beam is quite small, and one would need to do a mosaic of many pointings across the brightness distribution in order to recover the image. So that's another important detail. Okay, here's another interesting detail, the pixel size and the image size. So I haven't said anything about this. If you take an image with an optical camera, or say your cell phone camera, it has some number of pixels, you know, often some number of megapixels, and they're a particular size behind the optics, and you get that number of pixels in your image. Well, I haven't said anything about how many pixels there should be in the image you're making with this Fourier transform, and in fact, that's something that you have to decide. So the most important criterion that you want to satisfy typically is to satisfy the sampling theorem for the longest baselines. That is, you want to recover usually the finest detail that you've observed with the longest baselines of your interferometer. So that said, your pixel size needs to be half of 1 over the longest baseline, and in U and in V. In practice, people tend to use more pixels than that, maybe 3 to 5 pixels across the main lobe of the dirty beam, because that helps in deconvolution that I'll explain later. So if you're observing, say, at 870 microns, that's 345 gigahertz with baselines to 500 meters, that's what we do with the SMA often, that tells you that your delta L, delta M, your angular size of your pixel should be less than about 1/10 of an arc second. In the CASA software package, which is used for ALMA and the VLA, this pixel size is usually called the cell size of the image. So if you look at the software inputs, it usually says cell. Okay, so that's the pixel size, but what about the image size? I mean, there's nothing about the interferometer that tells you how big the image should be. So a natural choice is often the full extent of the primary beam. So that primary beam size that we discussed in the previous slide tells you where the response is falling off to some negligible scale. And so the primary beam size is maybe a good proxy for how big you want to make an image. So again, if you were with 6-meter antennas at 870 microns, turns out the primary beam size, the full width half max, is something like 35 arc seconds. And so you might want to make an image that's twice that, 70 arc seconds by 70 arc seconds. And then with pixel sizes, if your baselines were to 500 meters, of less than 1/10 of an arc second. You can get into trouble if there are bright sources that are in the side lobes of the primary beam. Then when you take this fast Fourier transform, which has periodic boundary conditions, it might alias some of that emission into the image. And so you might need to make a larger image to capture that response outside the primary beam, or you might be able to make multiple small images. There are a lot of different ways to deal with this problem. But this is another user parameter in CASA. It's called the in size. So these are decisions that you can leave it up to the software to make. After all, it knows something about the longest baselines you observed, and it probably knows something about the primary beam of your telescope. But these are also parameters that you can very easily change, and you may want to. All right, now there's another concept called the weighting function, which is very important as well. Okay, visibility weighting. So we have our sampling on the right of the UV plane, and you can imagine that you could modify that sampling function if you want, right? This is what the telescope gives you, but it's not exactly what you have to use. So you can introduce a weighting function, which here I call W. It's a function of U and V, to modify the sampling function. Usually it's just multiplied. And by modifying the sampling function, you change the little s, the point spread function, or the dirty beam shape. So there are various choices one can make. One choice, a natural choice, is called natural weight. So natural weight says that the weighting function is just 1 over the noise variance in the cells that are occupied in the UV plane and 0 everywhere else. So you're just weighting by the noise, effectively, of your observations. So if you do this, then you're getting the maximum point source sensitivity. That is, you're getting the most sensitivity you can out of the visibilities that you've measured, up for structures up to the size that you've measured. So this gives you the lowest RMS noise in the image. What it also does is it generally gives more weight to short baselines, that is the low spatial frequencies, because in any aperture synthesis observation, you usually have a centrally condensed set of tracks in the UV plane. You just have more visibilities for the same number of antennas concentrated into fewer cells. And so what that means is the angular resolution is not the maximum that you can get. It's somewhat degraded. But your sensitivity is the maximum that you can get. And so here's the Fourier transform of that sampling pattern for the so-called natural weight. It's a well-behaved looking function. But it's certainly not the only choice you can make. There's sort of an orthogonal choice called uniform weight. So uniform weight says that the weighting function is inversely proportional to the local density of points in the UV plane. So what does that mean? That means the sum of weights in any UV cell where there are observations is a constant, right? So you're not worrying about the actual noise that you've measured. You just give any occupied cell a constant weight. So what that means is the UV plane is filled more uniformly, and if it's filled more uniformly, that means the structure, the dirty beam side lobes, are lower. It also means you give more weight to the longer baselines, the higher spatial frequencies. So you get more angular resolution out of the same sampling. It also means that you're downweighting some data. So particularly in this example, in the inner part of the UV plane where we have lots of visibility points, they don't get to count for lots of visibility points because the weight in any occupied cell is just a constant. So that means the sensitivity to point sources is degraded. So here's, if you look at the bottom right here, there's the point spread function. If I compare it to the one at the left, you can see it looks different. And this works pretty well, except, so you're enhancing your angular resolution, you're giving up some sensitivity, and that's all fine. This can get you into a little bit of trouble if you have parts of the UV plane that are very sparsely sampled, because all of the occupied cells get the same weight. So you have to be a little careful if you have outlying samples, that they don't overwhelm the rest of the observations. But in general, uniform weight's a perfectly valid choice. There's yet another scheme called robust weighting. This is often called Briggs weighting after Dan Briggs, who was one of the inventors of this. It's actually kind of amazing. So this is a variant of uniform weighting that essentially avoids giving too much weight to UV cells that would otherwise have very low natural weight. Every software package implements this in a different way, which is kind of crazy, but that's the way it is. So I don't know if any software package actually implements the following, but it's an easy way to think about it. If you imagine that the natural weight of a cell in the UV plane is S_n, then if you apply some threshold weight, then use this weighting function, 1 over the square root of 1 plus the natural weight divided by the threshold weight squared, then if you implement a high threshold, if you give S threshold a high value, then this weighting function tends towards natural weight. And if you give it a low threshold, then it tends towards a constant to uniform weight. So essentially this threshold is an adjustable parameter that allows for some continuous variation between natural weight and uniform weight, between the maximum point source sensitivity and the maximum angular resolution. What's magic about it is that, sort of counterintuitively, you can achieve almost all of the sensitivity and almost all of the resolution simultaneously. So it's kind of an amazing thing, and it's rather wonderful. But it's another decision that you, as the image maker, have to make as to what to use for this threshold value. So here's another thing you can do. It's very common, especially if you're interested in the larger scale structure from your data. You can just apodize the UV sampling by a Gaussian. Just multiply it by a Gaussian. That is, the weighting function is just a Gaussian, as expressed here, with some full width half max, some parameter which is usually called a taper. So if you're multiplying by a Gaussian in the UV plane, right, then that's the same as convolving by a Gaussian in the image plane. So it's a form of smoothing. And what it does is it downweights the long baselines and gives more weight to the short baselines. So you degrade angular resolution. It also downweights the data at long baselines. So your point source sensitivity is downgraded. However, it does potentially improve your sensitivity to extended structure, which is sampled only by the short baselines. So there are obviously limits to the usefulness of this, because if you taper away all your data, you don't have any data left. So if you're really interested in large scale structure, then you need to make more measurements at short baselines. But if you have measurements at a wide range of baselines and you're interested in the larger scale structure, you may want to taper away the small scale structure and focus on the large scale structure. All right. So it's a little abstract, so let me go back to the example here. So here are the point spread functions made with a bunch of different weightings. So this is actually from that example of UV sampling that I brought up before. On the top left is the natural weighting. And in this case, a fit to the core of the point spread function gives a beam size that's 0.59 by 0.5 arc seconds, and the RMS is 1 in some units, maybe millijanskis or microjanskis or whatever it is. And uniform weighting below that, you can see that the core is smaller. It's almost half as large, 0.35 by 0.30 arc seconds, but the noise is 2.1 in the same unit. So it's twice as noisy, but the resolution is much better. If you go to the upper right, this is using robust weighting with the robust parameter set in the middle of its range. It happens to be 0 for the software package I used here. And you can see that the angular resolution, 0.4 by 0.34, is almost as good as the uniform weighting. And the RMS, being 1.3, is much better than uniform and almost as good as natural weighting. So that's an interesting compromise if you're interested in sensitivity and small structure. On the lower right, taking the natural weighting and just multiply it by a Gaussian to get a beam size that's 1.5 by 1.5 arc seconds. And so this downweights some long baselines and the noise goes up, but this lower resolution point spread function might help if you're interested in large scale structure. And then of course you can combine these things in various ways. So here's a robust equals 0 weighting with a taper. And this taper was designed so that I get back the beam that's exactly the same size in the central core as for natural weighting, but you can see that the side lobes, the structure all around the central core of the point spread function is different. In fact, it's much better behaved. You can see in the natural weighting there's kind of a large skirt around the central core. That's much less visible here in the lower right with the robust plus the taper. It's a little bit noisier than the natural weight, but the point spread function is better behaved, and so that might be useful for deconvolution or for picking out sources that might be close together or otherwise overlapping point spread functions. So to summarize this business about visibility, weighting, and tapering, the imaging process gives you a bunch of parameters that provide you with a lot of freedom. And the appropriate choices of these parameters depend on your science goals. So if you're most interested in having the highest angular resolution, then you probably want to be using uniform weighting or a robust variant. If you're most interested in the best point source sensitivity, then natural weighting is the way to go. If you're interested in some extended source sensitivity, then you might need to do a taper. And you can see that you have all of these variations to work with. That is, there's not a single image that corresponds to your sampling of the visibility function. There are many different images depending on your choices of these parameters. All right, so this is great. You have an image, but as I discussed earlier, it's a dirty image, and it's hard to do science on a dirty image. And so you want to do something to improve that. Remember, the fact that it's dirty comes from the fact that you're missing samples in the visibility plane. And there's not much you can do about that other than getting more data. And it's inevitable that you're going to have missing samples. So there's a process called deconvolution, which tries to help with that. So I'm going to shift now from the imaging process itself to deconvolution. Right, going beyond the dirty image. All right, so if all those imaging parameters didn't scare you enough, then here's something else to keep you awake at night. There are, in fact, an infinite number of sky brightness distributions that are compatible with the samples you've made of the visibility function. Because you can invent invisible distributions where the point spread function convolves with the invisible distribution in 0. So let's think about what that means. There are different regimes that are easy to think about, I think. So one is there's no data beyond some certain maximum U and V that you've sampled. So that means there's structure in your source potentially that you have not resolved. And I think we're all familiar with that. You have so much resolution and there might be some structure below your resolution, and if you live with that, that's okay. There's another aspect which is less familiar. You have no data within some minimum U and V, typically. So that means there's a limit on the largest size scale that you've measured. This is not something that we have a lot of experience with in the optical typically, but in radio interferometry, this is common. There's a limit on the largest size as well as the smallest size. And then you have all these holes in between the minimum and the maximum, and those lead to all the structure in the point spread function, which are called the synthesized beam side lobes. In addition to that, there's noise, and so there's undetected or corrupted structure in the sky brightness distribution. And the bottom line is there's actually no unique prescription for extracting an optimum estimate of the sky brightness distribution from the samples of the Fourier transform that you've measured. So formally, there's nothing optimum. So you have to do something, and this something is usually a form of deconvolution. And what that means is you use some nonlinear technique to interpolate or extrapolate samples of the visibility plane into unsampled regions of the visibility plane. So you have these regions where you haven't made measurements, and you want to know, well, what's going on in those regions? And deconvolution is your way of estimating what's happening in there. And the aim is to find some sensible model of the sky brightness distribution that's compatible with the data. But it's not a unique model, and it requires some kind of assumptions about the sky brightness distribution to pick plausible invisible distributions that fill those unmeasured parts of the visibility plane. Okay, so I'll just say that deconvolution is a very active area. There are many methods, many different algorithms. New ones are in the mode of compressive sensing methods. But in radio astronomy, the dominant deconvolution algorithm is something called clean. And the a priori assumption of clean is that the sky brightness distribution can be represented as a collection of point sources. And the idea is that you fit and subtract the point spread function iteratively to the image, to the dirty image, and come up with a clean model. The original version from Hogboom in 1974 was purely image-based. Now there are a lot of variants of clean implemented in a lot of different software packages that have been developed for higher efficiency, to subtract the clean point spread functions and the visibility plane, to deal better with extended emission structure, and many others. And I'll show an example. But clean is pretty much what's generally used. There are other deconvolution algorithms that are used. One that used to be used more but is rarely used now is maximum entropy. And the a priori assumption there is that the sky brightness is smooth and positive. So what does smooth mean? Well, you have to define smoothness by some mathematical expression that is often related to entropy. And your goal here is to find the smoothest image consistent with the data, with the visibility samples. And there's a lot of exciting literature about the deep meaning of entropy as Bayesian information content. So maximum entropy is pretty cool, but it's not used that often. Pretty much now everybody uses clean. So I'm going to describe clean in a little bit of detail. Here's what the algorithm does. All right. So remember, you have your point spread function here in the upper right, your dirty beam, and your dirty image in the lower right. So what do you do to clean the dirty image? So you initialize a residual map to the dirty map, and you start a list of so-called clean components. Now what you do is then you go to the dirty image and you identify the highest peak in the residual map, which starts as the dirty map, as a point source. And you subtract a fraction of this peak using a scaled version of the dirty beam, of the point spread function, scaled by a so-called gain factor. Then you add this point source location and its amplitude to the list of clean components. And then you go back to the residual map and you say, well, what's the next highest peak in the map, and subtract a fraction of the point spread function. And then you go back and you keep doing this process over and over again. When do you stop? That's a good question. So a common stopping criterion is to say, well, the residual map maximum is below some threshold value, which is a multiple of the noise. If you're limited by noise, then you don't want to be cleaning all little peaks that are just noise. You just want to clean out the signal. So say when you get to 3 times the noise or 2 times the noise, you stop adding clean components. Another common stopping criterion is if you have an image, a map that's not limited by noise, but limited by so-called dynamic range, so that you have very bright sources and there are artifacts of the point spread function everywhere and they're way above the noise. So there you might just stop at some threshold, which is a fraction of the maximum. Say you get to 1,000 of the peak and you just decide you're done. Or sometimes you just stop when you get to some number of clean components. That doesn't really have any justification, but people do it sometimes. There's an adjustable parameter in this process, the gain. Typically, the gain is a small number like 0.1 to 0.3. If the emission is smoother and you need more point sources to represent it, then the gain can be even lower, maybe 0.05. One of the nice things about the clean algorithm is that it's easy to include a priori information about where to look in the dirty map for clean components. So these are often called clean boxes or clean masks. If you know all the emission is in a certain area, then you don't have to look all over the map for peaks. You can just look where you know there's signal. This is incredibly useful. It's also incredibly dangerous because you may or may not know where the signal is. So you really have to be sure of yourself. And I'll just add that, amazingly enough, using some higher mathematics that I really don't understand, Schwartz showed in an incredible, interesting paper that this clean algorithm is equivalent to a least squares fit of sinusoids to the visibilities in the case of no noise. So in general, astronomical observations do have noise, and so this proof does not apply, but it does give one some confidence that at least we're doing something that might be close to a good idea. All right, so there's still another step to the clean algorithm. You have your list of clean components, your residual map, which is cleaned down to noise. What do you do with that? Well, the last step is to make a so-called restored image. That is, you make a model of the sky brightness with all of your point source clean components. So you put all these point sources in your map, and then you convolve them, typically with an elliptical Gaussian, which is fit to the main lobe of the dirty beam. This is called the clean beam. It avoids the super resolution of the model, right? The model is all point sources, so it has more resolution probably than your observations. So you sort of smooth all that out to something that's closer to the longest baselines that you've measured. And then as a final step, you often add the residual map of noise, and that may include source structure below the threshold that you haven't cleaned. And the resulting restored image is an estimate of the true sky brightness, your T of Lm, that you can then do science on. And the units of this image are mostly Janskys per clean beam area. So it's equivalent to an intensity or a brightness temperature. So you clean your dirty map by iteratively subtracting point spread functions, and then you take that whole list of locations and point spread functions and amplitudes, and you put them all back together and convolve them by a Gaussian and add the residual noise, and you have your clean image. So for most weighting schemes that I mentioned, there's some information in the image from baselines that sample higher spatial frequencies than the full width half max of the clean beam, that is that elliptical Gaussian fit. So it's often the case that some modest super resolution is okay. But something to think about is that this restored image actually does not fit the observations, right? We've gone through this whole process. It doesn't actually fit. All right, so that's a lot of words. Let me show you some pictures. Hopefully this will help make the clean algorithm more clear. So here on the left, we have our dirty image. In the center, we have our list of clean components as an image. And on the right, we have the residual map. So if I run the clean algorithm, right, I start looking for peaks in the residual map, and say I do 30 components, then you can see in the central panel here, I hope you can see there are a bunch of little dots. Those are delta functions that correspond to the clean components that we found in the residual map. And then the residual map has had those subtracted with a loop gain of 1/10. And so there's still plenty of emission left, but we're building up a model of the sky brightness. So we keep doing this. Here are 100 clean components. now you can see the residual map is getting down closer to the noise. And here are 300 clean components. So now there's even less left. And this is 583 clean components. Why that number? Because I told it to stop when I got to twice the noise. So the residual map is essentially all noise now, and we have our 583 clean components, and I can make a restored image now by convolving that by a Gaussian and adding back the noise, and it looks like the following. So that image is something unlike the dirty image to the left that you can imagine doing science on. It's conventional to include a little ellipse, which is the clean beam full width half max, to give you an idea of what the resolution is. So to summarize, the final image that you get depends on a lot of the imaging parameters, right? The pixel size, the visibility weighting scheme, the gridding functions, and the deconvolution that you do. What algorithm, clean, how many iterations, what clean masks or boxes you use, and when you stop. So that's a lot to take in. You just have to remember that you've made measurements of samples of the visibility function of the sky brightness. If you want to know what the sky brightness is, you have to go through this process of imaging and deconvolution to get an estimate on which you can do science on. If you use the CASA software, which you might if you're using the Very Large Array or ALMA, I'll just mention that when you run clean, you get a whole bunch of files. What are they? You get something which is the final clean image. You get something which is the point spread function or the dirty beam. You get an image of the clean components. You get the residual after subtracting the clean components. And you get something called flux, which is the relative sensitivity on the sky, unless you tell it to divide by that. So there are a lot of different parts to the image that you get in the end. So if we take our example and we just look at the results from different weighting schemes, you can see the upper left we have the natural weight, the bottom left we have uniform weight. And you can see the difference there is mainly in the resolution. And the uniform weight is noisier, right? A little bit more than a factor of 2 noisier. But if you were interested, for example, in the size scale of the ring, if you were going to measure that off the image, then you'd want to have that high resolution. The robust equals 0 image is a good compromise between the two, and the natural weight image with a taper to 1.5 arc seconds, doesn't resolve the ring at all, but it is sensitive to larger scale structure, which you may or may not be interested in. And just to give an example from the literature, from my colleague Sean Andrews at the CFA, one of these was the actual sampling that I showed you. If you look at the second set of 3 panels here, in the left column, there are 2 images of this thing called WSB60, and the big image is a blob, and in the little inset you can see there are 2 peaks. So these are 2 images that are made from the exact same data, but we show both of them because we want to show the small scale structure and the large scale structure together. And it's hard to do that unless you use different weighting. So depending on your science, you might want to show one image or another image or both images. I mentioned there are a lot of variants to the clean algorithm. The basic clean algorithm is entirely scale-free in the sense that it treats each pixel in the image as an independent degree of freedom, right? It has no concept of source size. You're dividing up your sky brightness emission into point sources. However, in many cases, adjacent pixels in an image are not entirely independent. That is, if you imagine you had an extended source that covers 1,000 pixels in the image, it might be characterized by just a few parameters, right? Not 1,000 parameters. I mean, if you could characterize it by an elliptical Gaussian, for example, that just has 6 parameters. There's a position in 2 dimensions, there's an amplitude, there's a size, full width half max for the major and minor axis and an orientation. So you may not want to decompose that into 1,000 point sources. So there are deconvolution algorithms that are scale sensitive in the sense that they try to employ fewer degrees of freedom in order to model plausible sky brightnesses. And in CASA, there's a multi-scale clean, there's an adaptive scale pixel clean, and my experience is that these yield very promising results on extended emissions, because it's often very hard to decompose a big smooth thing into a lot of little point sources, but it may not be so hard to decompose it into a bunch of broad Gaussians, for example. So these are a little harder to drive because there are more parameters. If you have multi-scale clean, you have to tell the algorithm something about the scales that you're interested in, or you can let it decide, but there are more parameters regardless. But this is an area, again, of very active research and is leading to better images. All right. I want to say a little bit more about invisible large-scale structure because I think this is really important. So missing short spacings, that is, missing samples near the center of the UV plane, can be very problematic in radio interferometry because you're missing the largest emission scales on the sky. So how do you deal with that? Well, I think in general, it's important for any observation to estimate what the problem is going to be beforehand. So you might simulate the observations based on the baselines of the interferometer that you have, or you can check simple expressions for a Gaussian or a uniform disk, and one location of that is in a paper I wrote long ago with my PhD advisor, 1994. The reference is here. And here's a homework problem you can work on. If you ask the question, by what factor is the central brightness reduced as a function of source size due to missing short spacings for a Gaussian source characterized by some full width half max theta half? So the answer is, for a Gaussian source, the central brightness is reduced by half when this size scale is something like 18 arc seconds for 100 gigahertz at a 15-meter minimum baseline. So that's actually not a very big source. And if you want to see the derivation of this for a Gaussian or for a uniform disk, you can go to the appendix of this paper that I showed you, but it's kind of a cool problem to work out. If you can work out that, it's a bunch of Fourier transforms, then you will have understood the nature of the problem and a lot about imaging in interferometry. So let me just show you in pictures, though, a demonstration. The point here is that important structure may be missed because of the samples that you're missing in the middle of the UV plane. So here's the question. Do the visibilities observed in our example, our previous example, discriminate between these two models of the sky brightness? So remember, this model on the left is the one I've been using throughout the lecture. This model on the right is exactly the same, except there's a big whopping bright large source in it. And so the answer is yes, but only on baselines that are shorter than about 75 kilolambda. That is, if we have these two sky brightness distributions and we image them with natural weighting, well, you can see they're quite different. But if our samples were limited to 75 kilolambda and longer, then the images would look exactly the same, because that big bright thing in the lower right of the bottom sky brightness distribution is entirely invisible to those longer baselines. So one has to be quite careful. Let's see, I'm coming at the end of the hour, so I'm going to just quickly go through a few more slides and skip some. How do you find those short spacings? The easiest way to do it is to use a large single dish telescope. Remember, a single dish telescope of diameter d essentially measures all Fourier components from 0 to d, where d is the dish diameter. So you can make an image by scanning a single dish across the sky, and that gives you the brightness distribution convolved with the primary beam with the single dish response pattern. And if you Fourier transform that, then you get the visibilities out to the dish diameter multiplied by the Fourier transform of the primary beam response. then you can divide out that Fourier transform of the primary beam response, and you get estimates of the visibility function for all the baselines shorter than D. So if you choose D large enough, you have a big enough single dish to overlap with your interferometer samples, then you're all set. You've sampled all of the information on all size scales. Another way is to just use a separate array of smaller antennas. If the antennas are smaller, you can get them closer together. So you can observe shorter baselines that are inaccessible to the larger antennas. And in fact, you can use the larger antennas as a single dish telescope or a single dish telescope using the technique from the previous slide to measure more Fourier components that you can compare to the small ones. And a good example of this is ALMA, because ALMA has this main array of 50 12-meter antennas, which give you samples from 12 meters out to 14 or more kilometers. But then this compact array of 7-meter antennas, 12 of them, covers that range of angular scales that correspond to 7 to 12 meters. And it has 4 single dish antennas that cover from 0 to 7 meters. So now you've covered 0 to 12 meters with the compact array and more, and with the main array, 12 meters and beyond. And for the advanced of you, you can imagine mosaicing with a homogeneous array. So this is a big trick, goes to Eckers and Rotz, 1979. If you imagine an interferometer, it doesn't measure spatial frequencies at just a single baseline, in this case B in the illustration in the left. The dishes have a finite size, so you're really measuring spatial frequencies somehow between B minus D to B plus D. That is, the visibility that you measure is some linear combination of baselines that go from this baseline minus the dish diameter to the baseline plus the dish diameter. So somehow you'd have to unscramble this linear combination, and one way to do that is to mosaic, because the visibility depends not only on U and V, but it depends on the pointing direction. And so if you Fourier transform with respect to the pointing direction, then you can unravel some of this information. So if you understand that, then you're an expert. All right, I'm just going to skip to the end. I have some slides about ALMA. My concluding remarks here. This is what you need to remember from this lecture. Interferometry samples Fourier components of a sky brightness. You can make an image by Fourier transforming the sample visibilities, but it's not a great image because of the missing and incomplete sampling, and deconvolution attempts to correct for this incomplete sampling. So remember that there are an infinite number of images compatible with the visibilities that you've measured, and that missing or corrupted visibilities affect the whole image. You have to use some judgment in the imaging and deconvolution process, but it's really fun and it's worth the trouble because that's how you get high resolution images out of interferometry. So there are all kinds of things I didn't cover, so see the references for that, and thank you.
Okay, great. Thank you very much, David, for giving us this lecture. We hope you enjoyed it out there. If you have any questions, we'll leave David's email address, so feel free to contact him. The slides will be available on the ANITA webpage, that's anita.edu.au, along with the first lecture in this series, which was an introduction to interferometry, and a whole host of other lectures. We have some great ones coming this year, so stay tuned. But for now, we'll say goodbye and thank you again for listening.